So one thing I could do is look at a histogram of the wags variable. Uh, that's helpful to get a sense of the distribution of that variable. But I don't think I'm going to show you a really fancy version of the histogram function. Most of the time I use those functions just for my own use and not for like sharing with other people. But I thought it's not really a very good plotting demo if I never even mention how to look at a histogram, but I think that you're all already familiar with the hist function. Let's take a look at what the default box plot function has to offer. Box plot is a function built into R, and if I run it with this formula and this data specification, I get this. So the box plot function knows that when I do wags as a function of type, I want it to plot wags on the y-axis split by these categories, type categories on the x-axis, and I want to look in the DAT data frame to find these variables. And it gives me a separate box and whisker plot for each of the four types. So we can see that the Basenji seem to be doing the fewest wags here, but still plenty of wags. So this is a perfectly serviceable box plot, but maybe I would want to make it a little bit prettier. So I'm going to show what happens when I call exactly the same function, right? This is how this demo is going to work in most cases. I'm going to start by calling a function in a very simple way, like this, and then I'm going to call the same function again exactly as I did before, but with extra arguments, because I feel like it can be a little overwhelming when I have all of the arguments present initially. So here I'm adding one more argument, which is ylim, that I already alluded to earlier in the workshop, that specifies the extent of the y-axis. So in this case, I want it to range from 0 to 50, and ylab, the label for the y-axis. So now I'm going to call that, I'm going to actually print the word wags over next to the y-axis. So this is that version of the box plot. It's exactly the same information, but I've stretched out the y-axis to range from 0 to 50, and I've given it a string label. Maybe I would also like to do some other things with this box plot or with other kinds of plots. So for my convenience later, I'm going to calculate some vectors of means and standard errors of these variables. So the first one here is I'm calling m for means, and it is the result of this with function call, which you may not have seen before, at least not in this workshop. So I'm going to explain it for a second. I'm going to close the plot for a moment. You've seen tapply already. The tapply here, the call here has just 4 arguments, the same as how I've done it before. Wags is the vector, right, that comes from the data frame, and type is a vector of categories, of strings representing categories from that same data frame. Tapply is going to look at the values of wags for each unique value of type and calculate the mean of those values of wags for each unique value of type, with the one extra argument na.rm equals t, just specifying that when tapply calls the mean function, I want it to include this argument so that it will not give me a missing value for the mean just because missing values are present in wags. Instead, it will use only the valid values in calculating the mean. This is the tapply function call, right? I've embedded it in a call to with, and all that does with is a handy way of saying I want to do something using the data frame dat. So here, I've used attach for some of my stuff before, but now we're getting a little more sophisticated, so I decided not to attach dat this time. You can see it's not present in the search path. Instead, here, I'm calling tapply within a call to with, which says do the following with dat as the source of the names that are being used. So this whole thing calls tapply with wags and type as variables and tells R to find those variables within the dat data frame.
So is this any different than if you were to not use the with function and just put like dat dollar sign wags, dat dollar sign type?
No, it's exactly the same as that. Yep, it's just a
Okay.
way to avoid having to repeat that $sign
Okay.
over and over again. So in
Okay.
this case, it's not that much cheaper in terms of how much you have to type, but you could imagine situations where you would have that $sign repeated many, many times over, and it might be convenient to just say with dat at the beginning so that then you can avoid using the $sign thing many times in a function call. I embedded that in this plotting tutorial just because I thought it's a handy thing to know
Yeah,
about.
super useful.
Thank you for the question. Please continue to ask questions. I like that. Okay, so the output of the with function, which is really the output of the tapply function, is getting assigned to m, this new arbitrary variable name that I have. And I've mentioned this before, but maybe you forgot, so just in case, I put the entire assignment command in parentheses so that it will print the value to the console in addition to assigning it to m. So here is the result of the tapply function call embedded in the with function call assigned to m. This is now the value of m, and I can verify that by just printing m directly to the console here. But the parentheses around the outside of that are a shortcut to print it and assign it. And it's just the average wags for each of these 4 types of dog in this fake data set. And I'm doing the same thing here to get a vector of standard errors for each of those 4 types of dog. I just used the standard error function instead of the mean function. Remember, the standard error function is one I defined earlier, and it doesn't need na.rm equals t because it is built that way by default. Okay, so now that I have those 2 vectors available to me, I'm going to show you a box plot again. Here is that same box plot from before, plotting the distribution of wags for each of these types of dog. And I'm going to add some points to that box plot using the points function. So points will add points to an existing plot, whatever plot is currently active, which is that box plot right now. And its first argument, 1:4, represents the x values of those points. So these boxes are plotted at 1, 2, 3, and 4. I happen to know that is what the default box plot function does. Keep this in mind. When R is generating plots for you, it is always thinking of the space within the plotting frame as having numeric values. So even though in this case conceptually Basenji is not 1 and Beagle is not 2, for R they are. And in fact 1.5 would be the space right in between Basenji and Beagle. So that's handy when you want to add stuff to existing plots. So the x values are 1, 2, 3, and 4. The colon, remember, just generates a vector of integers ranging from 1 to 4. M is this vector of means that I already calculated earlier. So those are going to be the y coordinates of the new points that I add. And I'm going to use plotting characters number 16, and I'm going to color it blue. You can just learn what all the plotting characters are by trying them out or by looking it up online. 16 will provide a kind of a circle. So here is what happened after I ran the points function. It just added 4 points to the existing box plot, and those 4 points are the means for each of these types of dog for wags. And so now the thick black bar in the box plot is the median. That's what that's how a box plot is defined. But now we also have the mean visible in each of these plots, which is something that I find handy at times. And maybe I would like to add standard error bars to those means as well. So that's what I'm going to do with this next line of code. This packs a lot into into one line. Maybe I should have split this up, but I'll walk through it. I'm going to do something 4 times. That's what the loop part of this does. For I in 1:4, this is a for loop. I talked about this in the introductory portion of this workshop. This is just going to repeat a set of instructions 4 times, and each time it's going to temporarily store a value in the variable I, and that value is going to be 1, and then 2, and then 3, and then 4. And the instruction that it's going to repeat is this selected portion of the code. That's what falls within the curly brackets. And that instruction is a single function call to the lines function, which also adds stuff to an existing active plot, just like the points function did. So the lines function, here, what I'm going to do is each time I'm going to add a line that extends from one coordinate location to another. And the x coordinates are going to be I and I each time. So 1 and then 2 and then 2, and then 3 and 3, and then 4 and 4. And the y coordinates are going to be this. The line will extend from the mean that has that index I minus the standard error with that index to the mean plus the standard error with that index. Remember, the index I is going to be 1 and then 2 and then 3 and then 4, and there are 4 means and 4 standard errors, so it's just one at a time going to take each mean and subtract the standard error, and each mean and add the standard error, and draw a line connecting them. And the mean and the standard error represent the y coordinates for the line. The x coordinates are going to be at that location represented by I. So these are going to be vertical lines that have a starting and ending point with the same x coordinate. And the color is going to be blue, and LWD is just the line width. I made it 2. The default is 1. It's a little thicker. That's kind of a lot. In retrospect, I probably should have split that up into a few steps. But here is what that does. I ran that loop. It called the lines function 4 times and added 4 lines to the plot. And you can see them there. Now each of those blue dots representing the means for these 4 dog types for their wags has a vertical line representing one standard error above and below the mean for that type of dog. And as a reminder, the reason that worked is that the x coordinates I, 1, 2, 3, and 4 already represented the locations of these 4 dog types. I already knew that they were plotted at 1, 2, 3, and 4 along the x-axis. The y coordinates I had previously calculated as being the mean and standard error for each type, and they were in vectors of length 4, so I could retrieve the first, second, third, and fourth element in sequence as I was attempting to plot at the first, second, third, and fourth position along the x-axis of this graph.